answer for this.
Hmm.
So, following figure shows spectrum of an ideal black body at 4 different temperatures, number of correct statements in the following. So we're given energy distributions over here, and the energy distribution is in a peak like this. Okay. Okay, so we're going to be having wavelength here, and we are going to be having intensity. Now, why am I writing it as intensity and not as energy distribution? Think, tell me why.
Intensity includes its energy per unit area and unit time. So
See, because energy distribution is not a very sensible term there actually. Why? Because energy per photon. Now that you know what a photon means, right? You are not Planck. You don't need to think like what Planck thought, right? This was what is it? Planck's black body radiation curve, correct?
yeah,
But why should you think exactly the way Planck thought? You can adjust your scenario here to understand what this truly means over here, what energy distribution truly means. So you know that light exists in the form of photons.
yeah,
You know that energy per photon is going to be given by a formula h into c by lambda. That means if I'm going to be having increasing wavelength, what does that tell me about the energy there?
decreases per photon.
Right. So the energy of the photon is going to be decreasing as you go more and more in terms of wavelength over there. Now, the game here is like this. You're given 4 different values of energy distribution there. So the intensity here is also not a proper thing here. Why? Because when you look at the curve which Planck has gotten there, energy distribution, let's first understand what that means first. The energy distribution, if it was going to be perfectly, let's say, as expected, what's supposed to happen there? If it is following something where the intensity is going to be the same, intensity na number of photons, correct?
Yeah.
So if you say the number of photons and each of them is going to be the same, I should be having a graph which is going to be a proper curve where the peaks will be like this.
Yeah.
Right, it has to be on 1 by x. Right. So if it is going to be 1 by x, the curve should have the peaks of the curve lying on these points here.
Yeah.
Yes or no?
Yes,
If
sir.
intensity is going to be the same, that is intensity is same, the number of photons is same, I should be having a curve like this, y equal to 1 by x curve. But what am I seeing over here? What do we see over here? That curve is shifted. That curve is being followed, but it is being shifted away, correct?
Correct, yes. Yeah.
You can see that the curve is still being followed. You're still having T1 being something where technically it's going to be for lower wavelengths. Right?
Yeah.
T1 ka peak dekho.
Yes, sir.
Where is the peak for T1 there? The graph is looking like this, right?
Yeah.
It's like this. So effectively T1's peak was here, T2 is here, T3 is here, T4 is here. So it is still technically following some sort of a line like that, but it is not following it properly.
Yeah. Yes, sir. Yes.
My guess is it will probably go that way. I mean, I've not drawn it properly, but I think you can see the general trend it's supposed to be following. It's supposed to go like this.
Yeah. Yes.
Now, the idea here is if it is going to be following a curve like that, it is basically shifting out slightly. What does that tell you here? What can you understand from it here?
Like, right.
It basically means
There's some
you're not getting the same intensity.
Yeah.
If you are getting the same intensity, it should have followed y by x.
Yes, sir.
You're not getting the same intensity, you're getting different intensities. That means some photons of wavelength are coming out more and more and more. Okay, let us now have a look here. So this is going to be talking at 4 different temperatures, correct? So if you're going to be looking at 4 different temperatures, this is at T1. temperature T1, T2, T3, and T4. Okay. So we're going to be given four different temperatures, four different types of scenarios are given here. So they're asking us which one is going to be the highest temperature here. T1 or T2 or T3 or T4. Now, when you're going to be having something like this, the idea here is how should you proceed over here? The easiest way to proceed here is you look at the peak. The peak is going to be corresponding to a particular wavelength. And usually the peak is also going to be corresponding to the maximum intensity as well, right?
Yeah.
If you're going to be having energy distribution as a scenario here, the peak over here should correspond to both what is going to be the intensity and generally the wavelength which is going to be obtained at that intensity. So if you look at the highest wavelengths which are being seen here, what you should notice over there is
Lowest energy distribution.
it is going to be decreasing.
Mm.
My lines are not proper, but
Mm.
it's supposed to be properly in that direction. T1, T2, T3, T4, you're supposed to be having what to say wavelength decreasing, but at the same time you're also going to be having intensity increasing for that. That means temperature T1 should be the hottest. For instance, if you're, let's say I'm going to be taking a tawa and I want to stick it in the on a stove. If I stick a tawa on the stove, what will happen there?
You get heated.
What will be happening? The tawa will keep getting hot.
Yes.
As the tawa gets hot, what types of hot will it keep getting? It will start off with something like say red heat.
Red.
Then it will start going into white and then finally blue.
Yeah.
Something of that sort at least. So
Yes.
basically, it's going to be decreasing its wavelength, which is going to be shining brightest.
Yeah.
That is, the intensity is going to be talking about which one is going to be shining brightest over there. Is that logical?
Yes.
So the intensity talks about which one is going to be shining the brightest. Fair. But at the same time, the wavelength is going to be something which is going to be telling how much energy is thrown out. The lower the energy of the lower the wavelength over there, the greater the total amount of energy which is getting thrown out over there, which means the object is hotter.
Yes.
Only when it is hotter, it has got more extra energy to throw out, which is why it's going to be throwing out more energy there, right?
Mm.
So that is basically how you basically proceed to check out that particular thing. Which means in this case here, when it comes to the heat of the objects over here, the temperature at which they are present, T1 is going to be greater compared to T2, compared to T3, compared to T4. That is going to be your case over here.
Okay.
Now, so in this case here, option A is unfortunately wrong.
Yeah.
They're asking number of correct statements. So option A is wrong. Let's look at option B. Option B, the black body consists of particles performing simple harmonic motion. Of course, every object is going to be consisting of particles which are performing simple harmonic motion. So this is of course going to be true.
That's
C,
it.
we're going to be having the peak of the spectrum shifts to shorter wavelength as temperature increases. Of course, correct.
Yeah.
That's what we just discussed right now.
Yes, sir.
So this is going to be correct as well. D, we're going to be having T1 by V1. V here I'm assuming is not really V but frequency, correct?
Frequency. Yes, yes.
Is equal to T2 by V2 is equal to T3 by V3. What does that tell?
Inversely proportional.
Yep.
I mean,
No, not really. But what is T there?
lambda.
T is signifying total energy dumped. Correct?
Yeah.
Energy distribution. Look. So the T is signifying total energy dump. So if I'm talking about T1 or T2 or T3 or T4, that is total energy distribution. Total max peak energy distribution.
Yeah.
This means this is going to be hc by lambda into the maximum number of or the intensity which corresponds to maximum photons, correct?
Yes.
So this has to be hc by whatever lambda multiplied by whatever is going to be my number of photons for max intensity. That is basically what this is going to be. So in this particular case here, let's now look at what is going to be T by nu. So C by lambda is nu, correct? So I'm going to be having this as h into nu multiplied by this number of photons aspect here, which I'm going to call as n.
Yeah.
So if I'm going to be taking this is my t here, correct? So if I divide this divided by nu and nu will cancel.
Yeah.
Meaning I will now be having T1 by nu1 being equal to what here? It will work out as h into peak of intensity n, number of photons associated with that for nu1.
Hmm.
Correct?
Yeah.
And that is basically what it's going to be for each of the other cases as well. So it's going to be giving me some way of measuring the number of photons.
Okay.
This is going to be a type of measure for number of photons. Or you can think of it as number of individual light particles. Don't think of it as a photon. Now go back to how, what to say, Planck should have thought of this, because it's black body radiation, correct?
Hmm.
So at that time, Planck did not know what was a photon,
Yeah.
because Planck was the first dude who defined a photon, correct?
Yeah. Yes, sir.
So now you start thinking, break down, this is what we think of it, exactly
Hmm.
speaking now.
Yeah.
So now you revert back to what Planck thought of this particular thing as. This was what he thought of as type of measure for number of light particles. For number of light particles. Which is why this is going to be very fundamentally brilliant thing. Why? Because this talks about the number of particles of light in each case,
Hmm.
number of pieces of light. So if the intensity was the same in each of those cases, all of them are going to be the same. That is this n over here, which is going to be number of photons for max intensity. If that is going to be the same, then you'll be having the same value for sure. That's the idea here. So
Hmm.
option Delhi, I have no idea. My guess is he would have maintained same intensity. If he had not maintained same intensity, this would not have made a meaningful observation over there. So he would have tried to have maintained same intensity. So most probably that Delhi would have been correct over here according to Planck's measurement, depending on what he did there. Mostly this is going to be experimental circumstance.
Sir, but then there's like in physics we learned that there's Wien's displacement law, right? So that
I do
says
not
that,
know that laws. You tell me the graph for it, then we'll talk.
so it's not like it's like lambda max into t is constant always.
Lambda max.
Into t is equal to b.
Lambda max is going to be the wavelength of the substance emitted maximum.
Yes, sir. Yeah.
Okay, into
T temperature at that of that
that will
point.
not be sensible. That is not a correct law. That is something which is not something doesn't click over there. That is probably an approximation.
1 second.
Confirm if
Yes,
it
sir.
is perfectly correct.
Lambda max
Approximation.
wavelength peak is equal to into absolute temperature is equal to constant.
Give me the exact thing. Lambda max into.
T is equal to b. Lambda max is wavelength peak and T is absolute temperature.
That's what I'm trying to say. There is no lambda max meaningfully. Think for a second. Think for a second. Is this making sense? Is it?
Lambda at maximum,
That's what I'm trying to say. This is not correct. Anyway, give me the full statement. I will prove it to you. Give me the full statement. Lambda max into T is equal to
constant b.
constant B.
Yeah.
Now, this is something which is absolutely for sure an approximation. Now, why am I saying this is a random approximation and is meaningless? Which is probably why we do not study this in chemistry. Lambda max. What do you think lambda max is going to be? What is the definition of lambda max? Go into it.
The
The
wavelength.
maximum wavelength we can observe.
No, I think it's the wavelength peak, right?
Okay, so this is not the wavelength. This is a peak wavelength. That is a
Yeah.
T1
At
wala
the
wavelength.
top, yeah, exactly. That's a,
Oh, okay. That is a fair assessment. Then it is acceptable. Then it is
but
a fair.
then so then shouldn't T by mu be
No, this is an
constant?
experimental condition then. This is an experimental condition. That's all. This will probably bring up the same factor that intensity is going to be roughly the same. Basically, if you're going to be having this now, what does this tell you? T by nu is going to be a constant. T by nu is going to be basically number of photons for maximum intensity, correct?
Hmm.
I'm saying this is the same thing. These are same.
But then we don't know whether n is same for all the
Stop,
right?
stop, stop. Don't argue right now. I've already thought it through. If you want to argue, you mathematically argue. Don't give me some random shit. Now, what does this basically mean if it's going to be a constant? What did I get over here? We got T by nu will be equal to what?
Measure of particles
So T by nu is going to be H into number, correct?
with
Where this
constant
N,
matter.
what does this stand for? This stands for number of photons
Light particle.
of light,
Hmm.
right? This is what I'm talking about as intensity come measure, basically a number of photons of light which are going to be present over there. Now break it down. What is this T into lambda max? This nu is corresponding to that maximum frequency thing there, correct?
Yeah. Yes.
Wavelength scenario there. So if this is going to be the case here, I can effectively write T is going to be some constant divided by this particular lambda,
Hmm.
right?
Yeah.
Now, what is nu?
C by lambda.
C by lambda. So I'll be
Hmm.
getting this as T divided by C multiplied by the same lambda nonsense here.
Ah, yes. Yeah.
I'm going to be having H into N. I'll just take the C over here and multiply it over here. What do I get then? The
Same thing.
lambda into T is going to be HC multiplied by my N.
Hmm.
Basically, they're calling it some constant over here. I'm telling you what that constant is going to be. That constant is going to be HC into N. You understand what I'm trying to explain here?
Hmm.
That is, this is same as my lambda, as the lambda max which you mentioned, correct or not?
Yes, sir. Yeah. Correct.
So this lambda max into T actually works out as Hc into this N over here, which talks about number of photons of light. Now, instead of calling it as Hc into N, what did they call it over there? They called it as a new constant. What was the constant they called it over there?
B.
Tell ya.
B. Bombay.
Okay, so this is going to be called as P. So this is an experimental constant. This is not going to be something which is going to be anything else. So it's an
So then,
experimental constant.
and
Depending on how you plan your experiment, you can maintain this a constant.
no, sir. There's a value for that.
That's what I'm trying to say. This would have
Yeah.
been something which could have been controlled in an experiment. I'm
Mm-hmm.
saying that in the paper they published over there, they would have used it as a constant over there, which is going to be involving the maximum intensity which you can observe at that time.
By
Remember,
fixing it.
matters. Think, think for a second here. This is
Okay.
done at a much, much earlier time.
Yeah.
This is not really a constant. This B here is not really a constant. It is a constant based on the experimental conditions which were available at that time. Not
Correct.
any. I'm 100% sure we've got better systems where we can fire up lasers which are going to be producing much higher intensities. You agree this is independent on number of photons of light?
Yes.
If
Yeah.
I can plot a larger number of photons, obviously I'll be able to get a larger value of
Greater
B.
constant. Yeah.
So this is not really something which is going to be a meaningful observation, but it is an observation which will be holding good mostly when it comes to a particular small band of wavelengths. My guess is in the visible region. Not 100% sure in which region they were experimenting on. This
Yeah. I
is
think visible reason.
the
Like
constant.
visible
Basically,
reason.
you can control the number of photons. That's the idea. And you know that it is going to be a constant. That's the game here. So if you can
Mm.
keep the number of photons a constant over here, then you will end up having this particular what equation? T by nu is going to be a constant there.
So this is only for visible light
I do not
region.
know. I do
I
not
mean,
know.
it
It
is
depends
on
on that.
Google.
Huh?
On Google, it shows that the peak is only in visible light region.
Well, I do not know the reason why it is a constant, but I can make a guess as to why it is a constant and when it will be a constant. Your science is solid. It doesn't matter whether you know the experiment's name and shit and whatnot. You just need to know the data which is going to be produced over there. So I'm
Mm.
guessing this is working only for what to say visible region, correct?
I think so.
That's what Google is mentioning, is it?
I mean, they just gave the constant lambda peak is equal to, but then they gave peak to be like other places as well. Uh,
It'll work for a particular range, I do not know which range they were working on. It would definitely include visible. It might
hmm.
include a few of the other parts also, because remember, those guys are working on UV also at that time and a little bit of IR also. As the wavelength becomes larger and larger, it becomes more difficult to measure. IR would have been more complicated. But UV, though, I wouldn't be surprised if they were using UV also there. Anyway, this is basically going to be having a particular spectral range within which only it will be working. It is not a proper constant. It is going to be an approximation. Anyway, coming back to the last option there, the given spectrum could be explained using quantization of energy. Yes, the given spectrum could be explained using
That's what.
quantization of energy, absolutely.
Yeah.
So for the question here, E will be correct here. D is also correct here. So four options are correct. What is the answer given?
Answer given two, sir.
Two.
Yeah.
Let's have a look at the options there. A is gone there. Black body consists of particles performing simple harmonic motion. Peak of the spectrum shifts to shorter wavelengths as temperature increases. That is fine. T1 by nu 1, T2 by nu 2, T3 by nu 3. Question is what is nu, what is nu 1, nu 2, nu 3? I'm assuming it is going to be the same as that. In that case, it should be the same. Okay. Black body consists of particles performing simple harmonic motion. Even if we assume that they are not going to be considering it that way, technically, let's assume they are going to be considering it as electrons getting excited and de-excited. If we do it like that, then it is still going to be okay. We can neglect B, but it still gives answer as 3.
I'll just see the mains people.
This is a JEE mains question.
Yes, sir. Yeah.
Which years?
23.
23. Okay. What is the answer for it, dude?
Just a second, sir.
You know which paper also?
Yes, sir. Yeah.
Very nice.